Hello, everybody. Welcome to the session. My name is Yoon Dong-won. I'm a server programmer, and I currently work as an AI engineer for Game AI Lab at NCSoft. In this talk, I'd like to share our experiences on designing high-performance and high-quality solving method for inverse kinematics. And also, I would like to show our optimal system for this model. This system can be applied to animating a large number of characters in games such as MMORPG. This talk will be in 3 parts: background of the topic, model description, and system optimization. Then let's get started. Before we move on, what is inverse kinematics? Let's take a look at a 3-link arm as an example. 3 rigid links are connected by 3 joints. At the end of the arm, there is an end effector which interacts with the environment. For the end effector to catch the target, we have to move it to the target position. And to achieve that, we have to calculate 3 joint angles. This is called the inverse kinematics problem, or shortly, IK problem. Solving the IK problem is not simple. The more joints there are, the more difficult the problem becomes. And also, there can be multiple solutions. So, we need to choose the most preferred solution among them. So, how do we use IK in games? In games, IK is used to enable characters physically interact with the environment, such as feet landing on terrains or hands holding onto some object. For human IK, hip is usually set as a root. This definitely creates more realistic character animations. Our goal is to render animations of numerous characters like this with IK motions in real time on a game client. To materialize this, we have developed a demo program in which there is a rugged cliff and 100 characters climb up here with IK motion. Now let me explain how we designed and implemented this demo. Our character has 4 end effectors, which are both hands and feet, and there are 23 joints inside the body for full body IK. And to render at higher than 60 FPS, our IK server must finish its job within 5 milliseconds for each tick. So the first thing we need to do is to determine the right approach to the IK problem. There are 2 commonly used approaches: analytical approach and numerical approach. Analytical approach is cost efficient, but it is difficult to express the full body IK in a general form, and it generates limited range of motions. On the other hand, numerical approach can solve complex full body IK generating high quality motions, but numerical approach imposes high computation cost because it computes in iterative fashion. Therefore, both approaches are either too complex to generate high-quality motions or computationally expensive. But we have to find a high-performance IK solution which also generates high-quality motions. And this is why we came up with deep learning. Because, of course, there is also many difficulties here. I'm going to talk about how we solve these problems from now on. So let's go into the deep learning-based IK solver model. In machine learning or deep learning, when input comes in, the neural network just quickly computes and infers the desired output. Then let's take a look at our input and output data format. Our model will generate a motion which starts with the characters, both hands and feet, holding onto the cliff. And it climbs up until both hands and feet are on the cliff again. To generate this motion, the model receives current and target positions of both hands and feet as input. It is a total of 8 position data. And the model outputs the climbing motion data, which is composed of 60 frames. And this is equivalent to 2 seconds of animation. We first tried to generate motions with a single DNN, but it was designed very large in order to infer and generate a motion all at once. And this very large DNN consequently introduced expensive computation cost. And to make the matter worse, the quality of output motion was not good enough. So we have divided the problem into 2 simpler problems. For each 2 problems, we designed lightweight models which are trajectory DNN and pose DNN. In this way, the amount of computation was drastically reduced to the degree that it was under 1% of the single large DNN. And the quality of the motion was also improved. Then let's take a closer look at the process inside the algorithm. As the first step, input data is sent to the trajectory DNN, and it generates trajectories of route and 4 endpoints. A trajectory is composed of 60 consecutive position data that corresponds to 60 individual motion frames. Once we get 5 trajectories, we can get 5 position data for each motion frame. These 5 position data are the root and both hands and feet positions. Next, for each 60 motion frame, pose DNN receives the root and 4 end effectors positions and outputs 23 joint angles, which constitutes 1 pose. These 2 types of DNNs are very small sized, and together they solve full body IK with a low computation cost. But there is still a problem with it. In deep learning, basically there is noise in DNN output. And the noise tends to get especially bigger for small-sized DNN. In our case, noise from trajectory DNN caused the trajectory output to be crooked, generating trembling motions. So we smoothed them out using one of the curve-fitting solutions, which is cubic Hermit spline. Then the pose DNN receives smoothed trajectories and generates smooth motions. Here are 2 contributions we made. First, we achieved high performance by dividing a single large DNN into 2 lightweight DNNs. And second, we reduced noise in trajectories using curve-fitting solution and generated high-quality motions. In deep learning, DNNs can compute inference tasks only after they are trained. To produce high-quality outputs from DNNs, first, we need to train the DNNs with a very large amount of high-quality training data. In our case, we needed almost 10,000 high-quality climbing motion data for training trajectory DNN and pose DNN. How to get so much climbing motion data? Should I wear motion capture markers and climb Grand Canyon 10,000 times? No, I can't do that. Fortunately, when gathering training data, computation cost is less important. So we used numerical approach to generate training data. We gathered training data through the following steps. First, animators produced 1 reference motion that matches our preferred style. Second, based on this motion, we randomized 10,000 position sets. Each set was composed of 4 end effector and 4 target positions. And finally, we combined 1 reference motion with each position set and generated motion data using numerical approach. In this way, we could generate lots of high-quality training data from small seed data. While there are a small number of joints in two-bone IK, our deep learning-based model solves full-body IK. We apply the same trajectory to both two-bone IK and our model. Then let's compare the quality of the output motions of two-bone IK and that of our model. Here, a climbing man is stretching his legs in an unrealistic way, or gathering his arms like a mantis. As you can see here, two-bone IK is likely to generate unintended motions, whereas our deep learning-based full-body IK solver model generates our preferred and detailed motion. From now on, I'm going to talk about the system configuration and optimization for running our IK server. Now, we have trajectory DNN and post DNN, and we also gathered training data. We can train these two DNNs on a dedicated server, which contains deep learning frameworks such as TensorFlow. Once DNNs are trained, we can deploy them on game clients, where inference will take place for IK server. Here our interest is optimizing client-side inference. In order for our IK server to work, it needs to perform inference tasks for trajectory DNN and post DNN. For the general client system, DNN inference task can be computed either on CPU or GPU. Then which processor is more suitable for our inference task? Before we get to that, I'd like to talk about the 4 characteristics of our system environment. First, our two DNNs are very small sized. Second, the scale of parallelism for our inference tasks is relatively small compared to training. Third, game client requires quick response in generating motion frames. So latency is very important for our inference tasks. And lastly, in game client, GPU is busy processing graphics computation. Then which processor is more suitable for deep learning inference, CPU or GPU? The design philosophies are different between the two types of processors. CPU is designed for low latency, and it is optimized for sequential and complex code execution. It can execute all kinds of tasks very quickly. Modern CPU commonly has 48 cores that are fast, flexible, and independent. Each core can process different tasks at the same time. For that, it makes use of sophisticated control logic and has a large cache memory. On the other hand, GPU is designed for high throughput. It has hundreds to thousands of slower cores and is optimized for the execution of a massive number of threads that all do the same tasks on a large number of data. Therefore, basically, complex and serial tasks should run on CPU, while simple but massively parallel tasks should run on GPU. However, if the system has to frequently execute a small number of small-sized inference tasks, it is also a good choice to infer on CPU. This is a graph comparing CPU and GPU usage when running each of the 3 commercial games. For all 3 commercial games, the GPU usage is almost maxed out, but the CPU usage is only around 20 to 50%. While running games and performing inference on the same machine, we checked how much inference overhead is introduced on each 3 games. And for each game, we performed inference on both GPU and CPU. To simplify the testing process, we prepared our TensorFlow model and performed inference on it. When inferred on GPU, there was a distinct frame drop in games. On the other hand, when inference tasks were processed on CPU, frame rates are maintained almost at the same level. And also we checked inference throughput while running each of the 3 games. Inference throughput is the number of inference tasks processed within 1 second. As a result, we could find that inference throughput is also higher on the CPU. This experiment shows that if we perform inference tasks on the GPU while running game client at the same time, they compete with each other for the GPU resource. Therefore, the performances on both graphics and inference computation are degraded. On the other hand, when we perform inference tasks on the CPU, these do not place a heavy overhead on the GPU. So, the impact on graphics computation is minimal and vice versa. For this reason, we chose CPU for processing our deep learning inference task. To select library for inference computation, we tested commonly used libraries to compare the inference performance on CPU, including our naive implementation with C++. For each library, we measured latency of performing all the inference tasks needed to create 100 IK motions. Inference engine, which is a key component of Intel OpenVINO toolkit, took about 2 milliseconds, which is significantly faster than other libraries. We used the OpenVINO toolkit to integrate deep learning inferences into the game client. OpenVINO toolkit provides high neural network performance on various processors, including CPU and GPU. OpenVINO toolkit incorporates Deep Learning Deployment Toolkit, or shortly DLDT. And inside the DLDT, there are model optimizer and inference engine. This diagram illustrates the typical workflow for deploying a pre-trained deep learning model through an inference engine integrated with game client. After a model is trained in the various training environment, Model Optimizer converts the trained model into the intermediate representation format, which is called IR. On game client, inference engine loads this IR and computes inference task. The most important optimization is to compute as many inputs in batches as possible. A batch is a collection of inputs that can all be processed uniformly. For example, here are 4 fully connected layers with 3 inputs and 3 outputs. We can batch process these 4 instances because each instance has the same shape. In this way, batching performs multiple vector computations all at once, and this leads to a higher parallel efficiency. The early IK server couldn't process characters requests in batches. For every game loop, each animating character separately sends requests for next motion frame to IK server. Then IK server processes each request one by one. This is too time consuming, so we changed the structure to improve the work process to support batch processing. First, we created Batch Manager for gathering characters' requests. After Batch Manager gathers requests from animating characters, it bundles the requests and sends them to Batch IK server, where trajectory DNN and post DNN compute inference tasks in batches. In creation step, a DNN instance is optimized for a given batch size. Because of this, the NN instance always performs same amount of inference tasks. Meanwhile, number of inference requests is different for each game loop. So, the number of inference requests often does not match to the batch size. There can be two cases. The first case is when batch size is greater or equal to the number of inference requests. In this case, we can just infer once and ignore unused space. And in the opposite case, where batch size is less than the number of inference requests, inference tasks needs to be computed multiple times. Iterating inference task is quite expensive. Therefore, when creating network instance, we need to put a batch size that is large enough to finish inference task with a single execution in most cases. As I explained in the previous section, 5 trajectories from trajectory DNN was crooked. So we applied curve fitting to smooth it with cubic Hermit spline. The polynomial of cubic Hermit spline is defined as here. You can substitute t for any value between 0 to 1, and you can get a point on the curve. This calculation is simple, but it needs 25,000 calculations to create motions for 100 characters. So we need to check if there is an efficient calculation method. We can express multiple polynomials in one matrix form. For example, this is one matrix combining 6 polynomials, which solves 6 points for T0 to T5. In this form, T0 to T5 are constant. So, by multiplying great parts in advance, 6 points can be obtained by a single matrix multiplication at runtime. Meanwhile, inference engine is capable of processing matrix multiplications along with inference tasks. In previous model of batch IK server, the trajectory DNN and post DNN was processed in batches. But the curve fitting was processed separately in polynomial form. We converted these polynomials to matrix form and processed curve fitting in batches along with trajectory DNN. This optimization has reduced overall latency of generating motions by 34%. We have checked the latency of generating 100 character motions to find performance improvement through batching. In the first test, we computed the inference task one at a time without batching, while performing curve fitting in polynomial form. It took more than 4,000 milliseconds, which is extremely slow. For the second test, we computed the inference task with batching, while still performing curve fitting in polynomial form. Then the latency was drastically reduced to about 66 milliseconds. And finally, we processed curve fitting in matrix form along with inference tasks, processing both of them in batches. In this case, the latency was even more reduced to about 44 milliseconds. To check optimization results, we measured the latencies of cost for generating 100 character motions. One of the latency of trajectory and curve fitting, and the other is latency for generating 60 poses. In both cases, our IK server using OpenVINO was about 11 times faster than our naive implementation with C++. The graph on the right shows the cost of generating one motion frame by combining the two processes. As a result, the overall average latency was 0.73 milliseconds, and max latency was about 2 milliseconds to generate one motion frame for 100 characters. This is less than the latency of 5 milliseconds, and this satisfies our goal. This is our demo program in which 100 characters climb up a rugged cliff. Each character moves with both hands and feet touching the surface of the cliff exactly. On the other hand, the frame rate was stably maintained over 100 FPS. Then let me summarize our talk. The summary can be split into two parts. For the modeling part, using deep learning, we can quickly get approximate solution from the trained DNNs without solving the problem directly. But there are many difficulties, such as modeling the neural network, reducing output noise, and gathering high-quality training data. So we solve those problems like this. And for the system optimization part, usually in games, GPU usage is almost maxed out computing graphics calculations. So we processed inference tasks on CPU to make less impact on gaming performance. And we found that inference engine of Intel OpenVINO Toolkit provides especially high performance on CPU. Lastly, we processed curve fitting along with inference, trying to process in batches as much as possible. And this is our team. We are having fun researching and proceeding with game projects in the field of AI. On the last Tuesday, reinforcement learning team presented about pro-level AI agent for Blade and Soul using reinforcement learning technique. It will be available soon on GDC Vault. Thank you very much.